In this video, we're going to go over Lab 4.1, which is a 3-input prime number detector using canonical forms. So the objective of this lab is to actually start building basic logic circuits. So we're going to use sum of products and product of sum forms, but we're going to start off by using the canonical form. And remember that canonical means that you're not trying to minimize. So you're going to essentially create a minterm list, and you're going to create minterms for each output and then OR them together, or each output that corresponds to a 1, OR them together, and you'll have a sum of products. Or if you do it the alternate way for a product of sums, you'll create max terms and then you'll AND them together. And so these are unminimized forms, but they're really a good way to start getting familiarity with how to build these circuits on your breadboard. So after doing this, we're going to have experience building these circuits and be ready to build larger circuits. But before we do that, though, we actually need to put something on our breadboard so that we have the ability to drive in ones and zeros. Before, we've used the arbitrary waveform generator to drive in input patterns, but now we're going to be driving in a circuit that requires 3 inputs. And so the arbitrary waveform generator only has 2 inputs. So we're going to build a circuit that's called an LED driver circuit. And what this is going to do is it's going to allow us to use the little slider switches that are in our parts kit, and we're going to be able to flip those back and forth, and we're going to drive ones and zeros into our logic circuits. But we're also going to have them drive LEDs on our breadboard so that we can see what the input patterns are, and then we're going to have the output be driven to an LED so that we can see what the output is. And so we should be able to take, a truth table and build a circuit to implement it, and then we'll go through and flip through all the slider switches and watch the input patterns on the LEDs, and we should be able to go through all the input patterns and verify that the output pattern is correct. So after doing this lab, you're going to implement an LED driver circuit, then you're going to design and breadboard a sum of products canonical form circuit to implement a prime number detector. Then you're going to build the exact same circuit but using a product of sum form. And as you do this, you're going to run into an interesting thing which is called fan-in, okay? And you need to figure out how to address this thing called fan-in when you start implementing logic circuits in the real world. Okay, so the parts you're going to need, you're going to have your breadboard and wires, but this time you're going to build this LED driver circuit, and you're going to require your slider switch, you're going to require your 9-pin bust resistor that has 9 10K resistors in it. It's in a single inline package. You're going to need your resistor network that has 8 position 330 ohm isolated, which is a 16-pin dip. You're going to need 5 red LEDs, discrete, and then you're going to need 2 inverters, the HC04. One will be used in your actual circuits and one will be used in the LED driver. You're going to need 2 HC11 3-input OR gates. You're going to need 1 HC32 2-input OR gate. You're going to need 2 HC4075 3-input AND gates, and then you'll need 1 HC21 4-input AND gate. Okay, so there are 5 deliverables associated with this lab. The first one, you're going to demonstrate your LED driver. Then you're going to design and implement your circuit for the SOP, and then you'll design and implement the circuit for your POS. Okay, so each of those will be 2 steps. Okay, so let's begin with the LED driver. What we want here is a circuit where we can have a dip switch that when we turn it on, it drives a logic 1 to our circuit, but we also want to turn on an LED. Okay, so in order to do that, let's start with this little circuit right here. So this is a representation of your 8-pin slider switch. So on the switch itself, it has a label called on, and when you close it, you flip it into the on position and it closes the switch, and then you flip it to the other position, it opens the switch. So if you think about it, we could have VCC brought into the left side of the switch, and when we shut the switch, what'll happen is that you'll get a 1 right here. So if this point right here is labeled A, we will tie A to VCC, and that'll produce a logic 1, and that's great. Well, what happens when the switch is open? Nothing's driving A. So what we want to do is we want to pull it down to ground. So what we want to do is tie A to ground so that when the switch is open, it pulls it to a 0. The problem is that when you close the switch again, you would potentially have VCC connected directly to ground if you just wired this this line right here directly to ground. So in order to get around this whole problem of shorting the supply to ground when you have the switch closed, what you do is you put a resistor in series with the path. So if you think about it, we're going to put a 10K ohm resistor right here, and let's think about the operation. When the circuit is open, okay, the switch is not closed, A is just sitting here right here, and it is pulled to ground through a 10K ohm resistor. And that's fine, it pulls it down to 0. So that works. When you close the switch, A is pulled up to VCC, and current can flow from VCC through the resistor to ground, and the current will be very small because the resistor is large, okay, and due to Ohm's law. Now, the reason that works is that since the resistor is down here, and since we're shorting directly to A to VCC, it'll pull A all the way to VCC. When we pull it down, when we open the switch, since there's no current flowing, there's no voltage drop across the resistor, so we pull A all the way down to ground. So this is a very common way to handle switches. To implement the resistors, what's cool is that this little array, resistor array, is called a bus array. And so what that means is that there's 9 resistors in here, 9 separate 10K ohm resistors, but all of their bottom nodes are tied together. They're called bus. And the reason that's cool is because you can then tie that one node to ground, and that takes every single resistor and ties it to ground. That's neat because with one wire, we're able to wire all 9, one side of the 9 resistors to ground. Now what we're going to do is we're going to have 4 input codes that we want to create. So we're going to use 4 positions of the switch, and we'll tie, we'll label them A, B, C, and D, and then we'll tie all of those into 4 of the resistors to ground in this resistor array. Okay, that is easy. Okay, so we're going to do that, and we'll be able to drive in A, B, C, and D, ones and zeros depending on how we close the switch. But we also want to drive an LED. So wouldn't it be neat if we had A, when it's a 1, it would turn on an LED. The issue we run into is that we don't want to just hook a resistor and LED directly to this node right here, because then it starts drawing current and it affects the voltage that A is at. It would load A is what we would say. And we don't want to load A. What we want is A to be driving into the inputs of basic gates so that there's really no current being drawn. And that's neat because then A is always a rock solid VCC or a rock solid ground. So in order to do this, what we can do is we can put a basic gate on A over here, and the only basic gates we really have are inverters and AND gates and OR gates and NANDs and NORs. So let's use an inverter that will take A and it will drive a new version of A over here, and since there's an inverter, this is going to be A naught. So if we wanted A to be a logic 1 representing the LED turned on, a 1 over here would be a 0 over here. So how do you get an LED to turn on when you drive into the LED circuit a 0? Well, you put it backwards. Okay, so if we put VCC over here and then we point the LED this way through a resistor, if we have a 0 at this node right here, then the LED will turn on. If we have a 1 at this node, then what will happen is it will be at VCC right here, and it'll be VCC right here, right there, or at this side of the LED. There'll be no voltage drop across it, and the LED will be off. So by changing the direction of the LED, we can get the light to correspond to what we want, which is when A is a 1, the LED's on. When A is a 0, the LED's off. We do that for A, B, C, and D. And what's neat is we also have another type of resistor array, which is called an isolated resistor array. And so you'll see this 16-pin DIP package, and it's got 8 resistors in it, and they're all isolated from each other. And so this allows the layout to be a lot easier. Okay, the last remaining piece here is we got to have an LED where we drive the output of our circuit into an LED to see if it's a 1, it turns on, if it's a 0, it turns off. In this situation, what we can do is we want a 1 on the output of our circuit to turn on the LED. So in this situation, we face the LED in kind of the traditional way of the way we think about it, where a 1 is a VCC right here, it goes through a resistor, the LED is facing toward ground, and current flows and the LED turns on. So a 1 means the on resistor. If it's a 0, we have a 0 on the input to the LED circuit, a 0 over here, so there's no voltage drop, and we have it's off. Okay, so a 0 means off. So what we can do is we can have the top 4 resistors in our resistor array have the LEDs facing backwards, and they're driven by an inverter, and that allows these LEDs to be turned on without loading our inputs over here. And then the output, we don't need to worry about it loading because there's only one pin and it's designed to drive this thing. So this is the first circuit that you're going to build. All right, so let's take a look at my breadboard and an example of how you lay this out. So if you think about this, if you come over to the breadboard, you're going to see down here, forget these wires up here because that's for the second part. Here's your dip switch, okay, and you can, flip it back and forth, on, off, on, off. Here's your inverter. Remember, you need power and ground. And what you do is you take 1, 2, 3, and 4, and you're going to wire them over into 4 of the inputs of the inverter. Here is the bust resistor. What's cool about it is that you just put this thing right here, and it has pins that have a resistor to this pin down here, and you just pop those in there, and then you ground this bottom one. Okay, so the pin that is what you want to worry about, that's the common connection, is the one that has that little dot on it. So if you look at the resistor, or this resistor, it's the one with the dot. That's the point corresponding to the common node of all the resistors. So that's the one that you want to put down here and have that go to ground. Okay, so that gives us this circuit right here. And then if we go through the inverters, here is the 16-pin isolated resistor array. And the way that this works is it's just the resistors just go straight across. So an input right here comes through the resistor and comes out right here. So we tie the 4 outputs of the inverters over here, and then I jumper those over to here, and I have ground, or I have VCC connections here, and the resistors go backwards flowing into here. So to test this, all you do is, if you look at this, there's a little on position there. Here's an easy way to move these dip switches, is use a pen, but don't put the pen out, and it's got a little hole there. It's perfect for these things. So if I turn this on, notice that, let me move that out of the way for you. Notice that that LED comes on, that LED comes on, that LED comes on, that LED comes on, and then off, 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 off. That's it. So build that circuit first, and go ahead and take a short video, 2 seconds, of just this demonstration of just on, off, 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 off. And it shows that that circuit exists. Okay, so that's deliverable number 1. And I give you a picture of exactly, and I label everything in here, so you should be able to just follow along with that. Okay, it's time to design a 3-input prime number detector. Okay, so what is a prime number detector? Well, a prime number is something that's only divisible by 1 and itself, and we are going to not use 1 as a prime number. Okay, so technically 1 is not a prime number. So if we have 3 inputs into a logic circuit, that can represent decimal 0 up to 7. So if we converted that to a 3-bit binary code, we want the binary code corresponding to decimal 2 to be true, decimal 3 to be true, 5 to be true, and 7 to be true. So we're going to cycle through 0 to 7 using 3 bits, and whenever those bits represent a prime number in decimal, the output will be asserted. Okay? So to design this, here's what you do. You always do it the same thing. The first thing you do is you create a 3-input truth table for this 3-input circuit, and you list for the output column any rows that correspond to a 1. Okay, so for input code 2, which is 0, 1, 0, you put F is going to be equal to a 1. For input code 3, output is a 1. For input code 5, output is a 1. 7, output is a 1. All the rest are zeros. Okay. Then what you're going to do is create a minterm list. Now remember what a minterm list is. It's just use the sigma and you list the row numbers that correspond to an output of a 1. So in this case, it's easy. It's 2, 3, 5, and 7. But you do that because then you're going to create a canonical sum of product logic expression. Okay. Remember, a canonical sum of product is for each one of these input codes, you're going to create a minterm. So for the input code 010, which corresponds to decimal 2, you're going to create a minterm. Now remember what a minterm is. A minterm has every input, and it's inverted if the input code is a 0, that position is a 0, and it's left as a 1 if it's not inverted. So for example, if you had input code 010, you're going to have a minterm of A naught B C naught. Okay, and that's cool because that's going to be a circuit that you'll build. So you're going to first create the canonical sum of product logic expression, okay, and it's going to have 4 minterm expressions that are ORed together. So what I want you to do is build this up. So print this page off and actually write in here. So the first thing is draw the truth table out right here. Then you're going to create the minterm list. So you're going to say F is equal to capital sigma and then list the row numbers. Then you're going to draw the canonical sum of products logic expression. So F is equal to, A naught B C naught ORed with A naught B C ORed with A B naught C ORed with A B naught C naught. Excuse me, that last term is A B C. And then you're going to draw the logic diagram. So this is just straight up piece of cake. You draw whatever you came up with for the sum of product logic expression. Then you run into an issue, okay? Because you now need to map the logic diagram into your parts. Okay, so in your parts kit, you have all these basic gates. Okay, you got a 2-input AND gate, 3-input AND gate, 4-input AND gate. You have a 2-input OR gate, 3-input OR gate, and you have inverters. Okay, so if you think about your logic expression, you're going to need A, B, and C, which come from your dip switches, but then you're going to need A naught, B naught, and C naught. So that's fine, right? You can just use an inverter. So you need 3 inverters, but this part right here, the 74HC04, it has 6 inverters. So what you want to do is go to this logic expression that you drew, and you want to go ahead and draw a rectangle around the 3 inverters, and then label it HC04. And what that means is that you're going to implement those three inverters using this part right here. Okay, so all 3 are going to be in there. Then you're going to go to the minterm portion, and remember you've got 4 3-input AND gates, okay, that represent each AND term is one of your minterms. Well, now you need a 3-input AND gate. So do you have that in your part? And it's like, yeah, you do have it. Look at right here. The HC11 has 3-input AND gates. Now there's only 3 per part, but that's okay because there's 2 of them in your kit. So you're going to need 2 of these gates right here to implement the AND terms. All right. Then you get finally to the OR. And here's the problem with the OR. The OR is going to have 4 inputs. Now, why is that an issue? It's because you don't have a 4-input OR gate. You only have a 2-input OR gate and a 3-input OR gate. So now you have a situation that's called fan-in. Okay. You don't have enough inputs into the gates that you have to implement what you want. So you have to figure out how to address fan-in. Okay, well, think about how we can address it. It's not very difficult. What you want to do is you want to manipulate your logic expression in order to use logic operations for parts that you have. So think about your logic expression for that final OR. Okay, you've got minterm 2, minterm 3, minterm 5, and minterm 7, and they're OR together. That requires a 4-input OR gate. But if we use the associative property, we can simply, it's an equivalent expression as if you put these little parentheses in there and say, you know what, I can OR M2 and M3 together first, then I'll do M5 and M7, OR those together, and then if I OR those 2 operations together, I get the same thing. That's the associative property. The reason that that's powerful is because if you look at this, I'm going to have a 2-input OR gate here, 2-input OR gate here, and then a 2-input OR gate here. I can recreate the same logic operation using 3 2-input OR gates. That is how you break up the OR fan-in issue. Okay, so in your deliverables, as you do this design, you have this. Right here you drew this picture, you drew your logic diagram. You do a rectangle around your inverters and labeled it HC04. That means you're mapping those 4 inverters into one part, the HC04. Then you come over and you draw a rectangle around the top 3 AND gates and you labeled them HC11, and then you drew a rectangle around the bottom AND gate and drew HC11. That represents 2 HC11 parts or integrated circuits that will implement those ANDs. Then you're going to have a 4-input OR gate. So go back up to your 4-input OR gate and go ahead and draw a picture next to it that shows that you're going to have 3 2-input OR gates that'll break up that fan-in issue, and then draw a rectangle around those, and you need to figure out what part to use. Well, it turns out right here, it's the HC32. Okay, that's your design process. So go ahead, this sheet of paper right here, you have all your handwritten notes on there, and there's plenty of room on there. So go ahead and either scan it, take a picture of it, and save it as a JPEG, and I want to see, or you want to deliver that as your design process. So that's the second deliverable. Okay, then you're going to implement it on your breadboard. Okay, so let's take a look at my breadboard. And I came up here and noticed that I grabbed my A, B, and C from down here. Okay, and I brought those up here. This is going to be my inverter, my HC04. Here's my two HC11 3-input AND gates, and then here is my HC32, which is going to be my 2-input OR gate. Okay, and there's 4 of them on there. Okay, so what I did is I brought my 3 inputs up here, A, B, and C, and I created inversions of all of them, and then I used them to create my 4 min-term logic expressions within these gates. And you can do it however you want. What I ended up doing was I built the first min-term up here, and then since I needed, the first min-term was A naught, B, C naught. When I went to build A naught, B, C naught, what I did is I ended up saying, well, I got A naught right here, so I just jumpered it down right there using that purple wire. So however you want to do it, you build up those 4-input OR gates, or 4-input terms, and then you bring the 4 terms over here, and then you build a 2-input OR gate, 2-input OR gate, OR those together, and then this is my output right here. Now a little caution, what I would do is I would test at every step. So bring over your inputs, A, B, and C, and then test them by over here is where we're going to bring in the output to a circuit. So this right here is going to be, I couldn't reach the whole circuit up here, but so I just jumpered it to here, and then I'm going to jumper over. So whatever I hook to here will light up that LED. So watch, if I put it into a power supply, it lights up. Now I've already powered my board using the analog discovery. So I brought in my analog discovery right here, and power and ground, and I configured it to be 3.4. So you got to do that to turn it on. But then I can test if something's a logic 1 or a 0 at any given time by wiring into it. So if I wanted to test that A was working like the inverter, I could come up here and I could put it into A naught, and then when I come in here, A is a 0, and look at what happens. It's a 0 there, but it's a 1 there, and if I switch it over, A goes to a 1, and A naught goes to a 0. So I can test that interim calculation. So I did that for A naught, B naught, and C naught, and then I built each term for each min-term, and I tested them as I went, and then I brought all 4 of the min-terms over here, and I tested the final output. So now the final output, let me bring this over here, this is going to be my final output over here, and this is the demonstration when you go to breadboard it. So I want to run through all 8 possible codes. So I have A is going to be my most significant, C will be my least significant. So this represents 0, 0, 0, and the LED is not on. So 0, 0, 1, it's not on. 0, 1, 0, that's decimal 2, it's on. 0, 1, 1 is 3, it's on, and that's what I want. And then I go to 4, which is 1, 0, 0, it's not on. 5, 1, 0, 1, it is on, that's what I wanted. Then I go to 6, 1, 1, 0, it's not on. Finally I go to 7, and it is on. So the output asserted for input codes 2, 3, 5, and 7, I just built a 3-input prime number detector using a canonical sum of products form. The deliverable is take a short video cycling through all of these input codes. And if you use a pen, it's pretty easy. So it's 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1. Okay? 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1, boom. 3 to 5 seconds. Okay, so that's deliverable number 3. Now you're ready to build an exact duplicate circuit, okay, but using a product of sum form. So remember, a product of sum form is just an alternate way to build a circuit. So you start with a truth table. So I give you another piece of paper right here, and I want you to print it out and write right on it. Create the truth table. You already did the truth table. It's just to put it on this piece of paper, so that's clean start. This time, though, you're going to create a max term list. Now remember, a max term list is where you list the rows corresponding to an output of a 0. So we want this thing to assert for rows 2, 3, 5, and 7. That means a max term list would contain the rows 0, 1, 4, and 6. Notice there's still 4 max terms. Then you're going to create the canonical product of sums logic expression. Now what you're going to do there is that you design it, but you're going to create OR terms for each of the max terms, and they're each 3 input. And you're going to have 4 of them. Then you draw the logic diagram. You take those 4 max terms and you run them into an AND gate, so a 4-input AND gate, and you draw the product of sums logic expression. Okay? The next thing is you need to map the logic diagram into your available parts. So you say, well, I need 4 3-input OR gates to represent my max terms, and I need a 4 input AND gate. So I got fan in issues again. But this time you don't, because if you look at this, you have 3 input OR gates. So that handles your max terms. This time though, you do have a 4 input AND gate, so you can implement the product of sums directly without any fan-in issues. Okay, so then what you're going to do is you'll draw rectangles around all of the groupings for your integrated circuits in your parts kit, label them. Okay, you don't have fan-in, and then you're going to go ahead and either scan this page, take a picture of it, and that's deliverable number 4. Deliverable number 5 will be you are going to come back to your breadboard and you're going to build that circuit. When you do it, leave space on your breadboard to build the circuit right here. You can leave your inverter right here and reuse it, or you can move it down if you want. But you're going to have space right here to build your product of sums. And then you're just going to essentially, this will be your output, and you're going to test that circuit. Okay, so it should be identical to the sum of products functional behavior. It's just done in a different form. Take a short video of that, and that's deliverable number 5. And you have done it. You have created now 2 circuits. So after this, could you, if you ask yourself, could you describe the operation of an LED driver circuit that produces input codes to your logic circuit while simultaneously displaying the input codes and output code on an LED? And what I mean by describing that is describing how you had to use the pull down resistor on the dip switches and how the inverter caused the inversion of the input, so not to load it, but then you had to put the LEDs in the opposite direction. Could you describe that to somebody? Could you design and implement a canonical sum of products circuit from a word description? The word description was create a 3 input prime number detector. Could you implement the same circuit using a product of sums form? And could you explain what fan-in is to somebody and how you could address it? Okay, if you can do all those things, you have successfully completed this exercise.